And of course, as in most economic models, the goal is to maximize expected utility, lifetime utility. And here's U is the utility of consumption. And this is very common setup for economic models. You always put consumption into utility, not wealth. Economists don't believe that you get utility from having some wealth. The economists believe that you get utility from actually consuming part of this wealth. This is actually also kind of interesting assumption, because it does not ever explain the concentration of wealth in the top percentile of the wealth. No matter what economic model you use, if you put consumption here, it's impossible to obtain this concentration of capital that we actually observe in US and another country. You cannot explain that unless you somehow you put some indirect way you put wealth here. But here we stay with the mainstream model. It's a very mainstream model. We use utility of consumption here. And of course, the development of these financial intermediaries, they affect the economic growth, inequality, and wealth accumulation, and so on. So this is basic setup, and now we are going through probably 15 or 20 minutes of heavy math. Please stay with me. I will try to make it as painless as possible. So here's basic method of how we solve those economic models. It's called dynamic programming, and it has nothing to do with computers or programming. It's just a term to It's just a term to define a mathematical procedure to find the optimal value of something. If you took calculus, simple calculus, it's somewhere similar to taking derivatives and finding maximum and minimum of function. Only here we are not finding maximum and minimum of function. We are finding the optimal function. So it's not the value; it's a function that we are trying to find. So okay, so let's look at this very scary thing, and let's just block it here and block everything here. Just look at here. This is just the utility of consumption. Actually, this is capital that people have. This is savings. So this is just the consumption. Okay. This is the definition, actually. This is the definition of value function at time t. So you see it depends on the utility of consumption right now. And further, let's parse it further. Let's always, when you see something very scary and very long, complicated expression, try to parse it by piece by piece. So here, let's look at this part. Okay, so this is horrible notation, by the way. There are 2 marks here. And they mean completely different things. So it's very confusing. It's horrible notation, but it's widespread in economic literature. So we will use it here as well. So here it's actually not a maximum. It's a procedure to maximize this whole thing, subject to choosing this set of actions. So it's not the maximum. I mean, I have to stress it again. It's a procedure to maximize the whole expression. And how we maximize it? We choose the sequence of STs over time. And the second part is actually also very simple. This is, again, just forget about this one for a second, just look at here. This is the same thing as here, it just at the next time period, t+1. So it's a recursive kind of definition, and what this is actually, this is, you can understand it as a discounted marginal utility you get from consumption in the future. So this is utility from consumption today, and this is kind of utility of consumption in the future. And that makes a lot of sense. It makes a lot of sense that here we actually have capital. We don't have consumption, we have capital kind of as a variable, because when you consume something today, you do not really trade it against consumption of the same thing in the future. So if you buy ice cream today, you don't kind of think of whether you will be able to afford ice cream in 20 years in the future. You're thinking of kind of how this consumption today will affect your marginal future wealth in the future. So this is kind of reflects the psychological trade-off between consumption today and marginal wealth in the future. And okay, so this is basically it. And this is distribution of possible risky returns, and this is the so-called value function for participants, for those people who join financial sector. So here people actually have an option of choosing between whether to be in financial sector or whether not to be in financial sector, and they always are choosing the maximum because they're already there, so they're getting the best of both worlds. And as we see later, this actually, once you join, you're never worse off than when you not join. So once you join, you always stay in the financial system. So this actually simplifies a lot. So this one is actually get cancelled, and you only have this one in this part. And the wealth or capital evolves like this, so it's always a fraction. It's always how much you save plus expected return in future. And expected return in future is always the maximum of safe return and this risky return. So there is no individual risks for participants in financial sector. It's all insured by financial intermediaries. And you again, in this condition that Victor Zhorin imposed, you're always better off when you're in financial sector. Then you're always better off than if you're even better off if you're just using safe return. So again, remember that this theta t is a stochastic thing. It can jump off or whatever. There can be any kind of crisis and everything. But if you're in financial sector, you're always better off because you're kind of protected from the downside as well. And this is this is the definition of so-called value function, and this is the most important tool for dynamic programming related economic models. And once you find it, you basically know everything about economy. Because you know how much people save at each time period. When you know how much they save, no matter what aggregate shock they face, you always know how the whole economy evolves in the next time period and so on. So you can build the whole transition dynamic very easily. And this is value function for people who are not participating in financial system. And here you see that there is a value function. It has this minus q. And minus q is the cost that you pay to join the system. So here is actually very difficult to trade off the value function for the future time period because you don't really know where you're going to be better off. And this value function is for those people who never participate in the financial system, who never join the financial system. And those people experience individual shocks, they experience aggregate shocks, and they have this kind of value function problem. And here, of course, there is a different distribution of shocks. So those people are going to get always much worse outcome than people who are here. Okay, I hope it at least makes some sense. If not total sense, but at least some. And usually you try to solve those problems analytically if you can. It's very hard to solve those numerically, and the difficulty lies in that it's actually functions. So you have to find not just the value, you have to find the function. And there are, of course, infinite number of functions possible, and it's very tricky to find the function that actually fits into those equations. And fortunately, for some simple cases, it's possible to find an analytic solution. So, for example, for participants, we can basically guess the value function here. We can guess it. And this is actually from later paper of Townsend Ueda. The Zhorin, they use log utility. We use constant relative risk aversion utility. Here it looks like this. And if you just guess the value function in this form and then substitute it here, there is very simple algebra. It's really very simple. It simplifies a lot. It just takes, and finally you get the optimal savings for those people, which doesn't depend on the level of capital. So the savings are constant no matter how wealthy you are. And here's the value function. So we totally got this. And the value function looks basically like a square root. It's like this kind of function.